So, the subtests. With unit tests, each function is intended to test some specific functionality. One unit of functionality, I guess maybe you would say, I don't know. But it's to test some very specific functionality. And we learn that we don't want the unit test to start testing a bunch of various things, because then it becomes a little hard to distill if a test crashes and that test had like 20 asserts. Well, which one failed? Because all it will say is, this test, this method with the testing, it failed. But which one? If I've got all these asserts, which one? So we want our tests to be very separated. We want to test independent things, one nice thing a little at a time. But sometimes we're put in positions where if I want to test, for example, do I have an example here? Subtests. If I want to test like diameter, you might remember from like our cert tests, if I'm testing something, I don't want to just test it on one input. If I'm testing some function like Celsius to Fahrenheit, I don't want to just test one input. I want to test various inputs to make sure it works in various cases. I might want to test those like edge cases. What happens if it's 0? What happens if the input is 0? What happens if the input is like really close to 0 but not 0? What happens if the input is just some arbitrary input? What happens if the input's a float? All of those cases. So suddenly we're put in a position where, well, I want my tests to be testing these like independent things, nice little small things with one assert, but I also want my tests to test multiple different cases. So I could go and write, if I had like 5 different tests I wanted to have for diameter, for example, I could go and write 5 separate tests. I could totally do that. There's nothing wrong with it. But that's going to be a pain in the ass. But also, I don't want to write one test with 5 different asserts in it, because if I do that, I run into that issue of, well, as soon as one assert fails, it's going to tell me that function failed. I'm not going to know which assert failed. It's just going to tell me that the whole method didn't work. The whole test method didn't work. So that's no good either. So I'm kind of left in an annoying situation, because it would seem that what I would have to do then is write the 5 separate tests. That's a lot of work. I'm lazy. Computer scientists are lazy. So what we do in this situation is we use what we call subtests. So the subtests, now there are a lot of different ways we can do it, but really the easiest way, in my opinion, is this. We start with, here I've got a list of 4 different cases that I want to test. Test diameter, various spheres, returns correct diameter. I've got 4 different cases, and I put each of them in a list. And then I have my expecteds list. And the expecteds list is, well, the list of what the results should be in the respective index. So index 0 of cases should be index 1 of expected. Index 1 of cases should be index 1 of expected, right? You see the relationship there. So I could then write, in a loop, assert expected and the case diameter, where case and expected is each thing from case and expected. So I'm just looping over and checking that the case matched what it should be. But the important part here, the most important part of this example is that line on line 16 that says with self.subtest. Because what that does is it tells Python and JUnit, like, okay, I realize that we have a loop here. And the loop means run this code multiple times. So if the loop ran 5 times, or in this case 4 times, that's like I have 4 separate asserts. And I just finished saying, you don't want to test with 4 separate asserts, because if the test fails, it's just going to fail for that whole test, and I won't know which specific assertion it failed on. But when we write this subtests thing, what that means to Python is I know I effectively have 4 separate asserts here, but we're going to pretend they're fully independent. Long story short, this is the magic code we write to make Python treat each of these asserts as if it was a separate test. This right here can be your boilerplate code. You can copy and paste this and make tweaks to it for all of your other tests that you want subtests for. So here's one for there. Let's see if I can find, here, if I go, where did I have it? Unit tests, no, here. That's assignment 3. So I want to see if I can find the one for spheres, test sphere. So here's the one with diameter, but here's the one with checking surface area. And you'll notice it's the same format. I'm just testing surface area now. And here I'm testing volume. Here I'm testing distances, and so on and so on and so on. That's the general pattern you're going to use with the subtests. So if we go back, okay, let me make sure. Okay, often we have functionality we'd like to test on various cases, but it feels rather silly writing a whole new test for each case. Consider diameter. Which cases should be tested? Well, we want to check our edge cases in general case. So test if a sphere has origin at 0, when the origin is non-zero. But we may want to confirm that the center point has no impact on the diameter, so we want to test the sphere on arbitrary location 0. And so this is just basically emphasizing the various different ways we might want to test diameter. So to test all 4 functionality, we would have to write these separate 4 tests, but that's a lot of work, so instead we use this subtest thing. The takeaway here is the subtest. Now, this right here is going to be like the general pattern. Cases is a list of different cases. Expected is the list of different expected results. So the cases here would be the input. Now here, because it's a method, it's not really the input. It's the individual spheres that we're calling diameter on. And expected is the output we're expecting. The important bit here that we're talking about is subtest. So for I in range of that, case at index I, expected at index I dot diameter. I don't know why that is there. That really shouldn't be there. You'll also notice this zip. Raise your hand if you noticed the zip and wondered what on earth that was. Zip is a handy way of saying, okay, if I just wrote here, you know what? This is probably best explained with an example. Okay, if I did for thing in A, print thing, we see this, right? No big deal. Thing in B, we see this. No big deal, nothing shocking here. But what if I wanted both the information from A and B? I know they're both the same length. So if I want the information from both A and B, well, I can do like the length, the range of the length of B or something for I. And then we can do like A at index I, B at index I. Right? We could do that, right? But what zip allows us to do is this. It allows us to basically pretend that the list A and B are kind of like zipped together, and then I can treat each of the elements starting at index 0 as a tuple, and then index 1 as a tuple, index 2 as a tuple. Now here, I'm immediately unpacking the tuple into thing 1 and thing 2. But let's see what happens if I don't unpack it, basically just leave it like this. I hit run. Well, we see A and W, like they are packaged together as a tuple. Long story short, in this particular case, it's just a quick and dirty, easy Python-y way of looping over two lists at the same time and having access to elements from both of those lists. That's all. If you don't like this, you don't have to do it. You can do it with the indexing. Yeah?
What would happen if you did that but there was two different lengths?
If there were different lengths, let's see what happens. If you do it with A being shorter than B, this is the result. But what happens if I do BA? It looks like what it'll do is it'll just truncate whatever is longer away. There. So if one's longer than the other, well, it'll only loop to whoever the length of the shorter of the two is. Good question. That's another example of a question I didn't know the answer to offhand because it's a really specific Python-y question. Best way to find out the answer to those questions is see what happens if you try it. Nothing you write in Python will break your computer. You're not going to break your computer. And the good news is, even if you could, it wouldn't even break your computer, it would break Google's computers. Yeah?
I actually wrote the print statement by assigning it as a variable, and I had to close out of Colab in order to fix it.
Yeah, so that is redefining what that name meant. That is a common mistake. A quick way to do that, instead of having to close it out, is you can do runtime, restart runtime. That'll just tell Python, forget everything I told you and just start from, your code will stay.
Yeah.
But the runtime will be like, okay, forget the fact that you reassigned print by accident. Common mistake, I've done it. You see, I see it done all the time in labs. People will be like, why is it not working? And without really knowing, I'm going to be like, I have a feeling you may have accidentally, yeah. People will do it with other important keywords as well. It happens. You can do it with input too. Because watch what happens. Like, check this out. If I say input equals print, and then I say, suddenly input means print? What? That doesn't make any sense. Well, yeah, I told Python, hey, you know that function input? That means read input? Forget that. You're equal to the function print. And so now when I called input, it's doing print's functionality instead, which is rather ridiculous. Don't do this. This is almost always certainly a mistake. But now this is actually a funny thing. I was actually talking to a colleague about this today, how interesting this is. In many programming languages, you can't accidentally do something like that. Python has functions as something that can be assigned to variables. Let me just make this very clear. I made ASD, the variable ASD, I assigned it the function print. Then when I called ASD, with that parameter, it printed it out because ASD is print. Now, with this comes an interesting, valuable feature. Here is a function definition. Apply operator. To be clear, this has nothing to do with unit tests. This is an interesting note about functions in Python. I wrote a function called apply operator. It takes a, b, and op. What it's supposed to be is a will be some value, b will be some other value, and op will be some function, let's say. Some operator, let's say. So, all this function does is it applies the function that I pass to it, op. It applies that function to the inputs a and b, whatever they are. So, just to make it really obvious, there. So now if I go down here and I say apply operator 1 to add, what would you expect the result to be? Well, I'm calling the function apply operator with the value a will be 1, b will be 2, and op will be the function add. So op ab should give me back, well, 3. Because a is 1, b is 2, and what happens when you apply this function here, op, which is add? Well, that's just add ab, well, that's a plus b. I can then show up and go like, no, I don't want to add anymore, I want sub. Now it's -1. Because 1, op of 1 and 2 is, well, the difference between the two. That's all. So this is an interesting thing you can do in Python and not many other programming languages, which is kind of cool. There are some people that think this is the greatest idea ever. And there are those that think this is a terrible thing that is a recipe for disaster, never do this. You will eventually, inevitably fall into one of those two camps, time will tell, but it's an interesting thing you can do. There's a lot of value in this, but there also is a lot of potential for mistakes. One of the most trivial and painful ones is accidentally assigning the print function to something else, like you just brought up. All right. There. Okay, cool. It's possible to do multiple tests within a single test by just using a loop. However, without subtests, if one of the tests fails execution, the rest of the tests would stop, and we would not know which subtest failed. By using subtests, it'll ensure that all the tests run, and if 2 of them fail, Python will tell you which 2 specifically failed, which is nice. You'll also notice the almost equal in this particular example. Almost equal is a good way to check for comparing floats. Because, well, we're always worried about equality on floats and floating point precision. So almost equal is a built-in method that from the unit test class that allows us to be like, are they close enough? And I believe that 5 I have on the end gives me an ability to specify the precision. 5 was chosen by me because it's not particularly meaningful. It's an arbitrary choice by me. Yes?
That's the precision of the almost equal.
Yes. So like how many decimal places, I believe. Okay, running the unit tests. Now, the way you run the unit tests is very different depending on which programming environment you're using. For me, when I'm using PyCharm, that IDE I was talking about, let me open it up. PyCharm assignments, no, I don't want that one, I want this. Here we go. When I want to run these unit tests, I could just, run the whole thing, all the tests pass, great. In fact, it's kind of cool, I can actually run all of the tests in my whole project. Run all of them. 193 passed, great, cool. All the tests for all of the code for this course have passed, fantastic. When you do it on Colab, it's quite different. Because with Colab, there's a little extra work you gotta do, but it ends up being a trivial amount of work, which is great. So here's what I'm going to do. First things first, I'm going to, I guess I'll also probably need point 3D. So I'm going to take So here I have the point 3D class. I need the point 3D class because the sphere class needs the point 3D class because, well, the center point is a point 3D. So I need to define what a point 3D is before I can make use of it. I don't need this import because it's Colab. Great. So I'm going to hit run. And I'm going to hit run. Okay, so both of these classes are now loaded into Python. Python knows everything about them. Here's a bunch of assert tests. We can get rid of those. Do I have assert tests down here? No, I do not. Now I'm going to go and I'm going to go to my test point 3D because I'm going to want to test that as well. So I'm just make a new block right here. Okay, and test sphere. I won't need the import. The reason I don't need the import is because it's all right there in front of you in Colab. The import's necessary in PyCharm because they're different separate files. Don't worry about it. So here. Okay, I'm going to zoom out. I'm at the back. There's no way you can read this correctly, right? That's fine for right now. So, what I have here is this is the point 3D class written. Immediately below, I have the point 3D test class written. These are the unit tests for the point 3D class. All of them that I wrote. Here is the sphere class, all of it. And here is the sphere test class, the stuff we just talked about. And inside of it, we have test sphere, center point, returns correct point 3D, radius, diameter, surface areas, volume, distances of the edges, overlapping, equal test, another equal test, another equal test, the rubber test. There's a bunch of tests there. We didn't specifically look at each and every one of these tests, which is fine, because the point is learning about how unit tests work. So here we go. The trouble is, when I run a class, whether it's a unit test class or not, all that does, it's the same as like when I define a function and I run the block where the function is defined. The function doesn't run until I actually call the function. With a class, when I run the cell where the class is defined, Python goes, oh, okay, great, I know all about a point 3D and a sphere, great. But until I actually make a point 3D instance and start using it, none of that, we're not really going to see anything. It's going to be the same issue with the unit tests. I can run the unit test class, but nothing gets run until it's told to run that class. The way we do this is literally this line of code right here. Copy. I'm copying that line. I'm going to go down here to the bottom. Here. I'm going to run this line of code. Unit test.main argv equals list with only an empty string in it, verbosity 2, exit false. What does that mean? Don't worry about it. It's the magic code we use to run unit test. I'm going to hit run, and look at that. 20 tests ran in 0.04 seconds, and it looks like everything's fine. They're all okay, great. And you'll notice this actually ran all of the unit test tests. It didn't just run the 3D or the point 3D test or the sphere test. It ran the sphere test and the point 3D test. It ran all the unit tests we had in our Colab project. If you're ever wondering, how am I going to remember this line of code? You're not. Don't waste your time. One way to find it is to go to this unit test thing on the course website, or go to Google and type in run unit tests Colab. See if I can do a quick search here. Oh no, I don't want all this. No, go away. Of course, Google is being not helpful in proving my point on how easy it is to find whatever you need on Google. There you go, right here. There. Here's one website you can find it. I'm sure there's literally a bajillion others. So don't worry about memorizing that line to actually run your unit test. Just remember that you can find it on the internet. That line of code will not be on the test. Don't worry. It's magic code. And we see that all passed. Great. That's all we have to do. We see output looks something like this. Are all the tests passed? Now, let's go, and I'm going to change one of these tests. Now, a unit test can fail for two reasons. Either the test didn't pass because the function we wrote is wrong, or maybe we wrote the test wrong, which could very well happen. So both of which the test will fail. You won't know if it's because your test is wrong or if your function's wrong. But what I'm going to do for simplicity here is I'm going to go and just change this right here to be 9, right? I'm changing one of the expecteds for the point for the sphere. By changing it, one of those tests should fail because the test was written incorrectly, but that's not what's important right here. What I want to highlight is what would the output of these tests look like had one of the tests or multiple of the tests failed. In fact, let's go and change some of the other tests. And this is expecting that number because why not? So I'm going to run this, and we see fail, fail. It tells us a bunch of the tests pass just fine, but some fail. Fail. Test distance between edges, various spheres, return correct distance. Case, where y is 1, x is 1, y is 1, z is 1, and radius is 1. And x is 10, y is 10, z is 10, and radius is 10. Expected 9. 9 is not equal to 8.05255888325765 with 5 decimal places, and it tells me what the difference is. It actually told you. So remember with the assert something? All assert would do is if it passed, you'd see nothing. And if it failed, it would just be like assertion failed. All it does is tell you that something's wrong with that case. With unit test, look how useful the output actually is. It tells you what the input was and what it expected, and it told you that, well, apparently you were expecting it to be 9, but I got 8.0525 whatever. It tells you what the mistake actually is. It's way more useful than just failed. Right? This is a lot more handy. And then the other one here. Well, this one's a lot more obvious. 11,111 is not equal to 1. Well, yeah. So 2 of the tests failed. Yeah, they did. Because the tests were written wrong now by me changing them. We'll put them back. Nope. And we're all good again. Pretty cool. Unit tests, fantastic. On assignment 4, on assignment 1, assignment 2, assignment 3, I gave you those assertions in your code right before each of the functions you have to write that help you figure out if you're right or wrong. Assignment 4, I'm not giving you those assertions because they're just too cumbersome. You can't do that effectively anymore with the complexity of our code. But what I am going to do is give you the unit tests. You are provided with the unit tests for the classes you are to write and all the methods for them. And I also include in the assignment handout that magic line of code that says unit test.main verbosity argv and whatever. All you have to do is hit run in that cell to make it actually run the unit tests. So instead of using those silly, not overly helpful assertion tests, you have the unit tests now. And you don't even need to write them. I gave them to you just to help you understand if you're right or wrong with the code you write, which is pretty cool. That should not stop you from writing unit tests from now on for every other piece of code you write, as opposed to the silly, not overly helpful assertions. Yeah. So you see the output, if they fail, it's telling you which test failed, which subtest failed. If it's a subtest, it tells us what was expected, it tells you what it got, and just because it failed, all other tests still ran. And that's another thing with the assertions. When you have this giant cell where you've got function assertions, function assertions, function assertions, functions assertions, there might be a total of like 28 assert tests in your code. And if the second one fails, your code immediately stops running. The other 26 assertion tests didn't run. With unit tests, they'll all run, and it'll tell you which ones passed and which ones failed. It's far more useful than just assert something. Writing and running tests may feel like a lot of work. You might even find that it takes more time to write the tests than the actual function. Yeah. But remember, I don't give a shit if you write me a function and give it to me. I want you to write a function that's correct. Writing the function is step 1. Actually, it's step like 10, because before that you need to understand the problem, figure it out, start running it, start writing it, test it along the way, then you're done. Okay, great, you've got a function that you think is correct. Now, prove it with the unit tests. Well, the unit tests won't prove anything. They just give you darn good confidence that it's correct if they all passed. But don't think, oh, but the tests take too long to write. But that's a part of what you're supposed to do. Writing the function is only a bit of what you're supposed to do. The tests are there. Not to mention, a lot of, it is hilariously common that you write your code and you start writing the tests for your code. And before you hit run on the tests, because you're thinking about what the input-output should be, the various cases and whatnot, what all the cases for passing and failing the test should be, when even thinking about writing those tests, it makes you realize you have a mistake in your function you wrote even before you run the tests. Because you're like, okay, I need to test what happens on the edge case. Oh, I never actually considered the edge case when I wrote the function in the first place. So you don't even need the test to fail in order to know that your function was wrong. Writing code is only part of your job. Demonstrating that your code is correct to yourself or anyone else is a big part of writing code. There's also, people will talk about test-driven development. Test-driven development is the idea that you write your tests before you write your function. You know what your function is supposed to do, and based on that, knowing what it's supposed to do, I can write all my tests without writing the function. I can write my test going okay, if the input is this is the output. If the input's that, this is the output. If the input is this, that's the output, and so on and so on and so on. Knowing what the function is supposed to do is all you need for writing the tests. Writing the function is, filling in the blanks. Knowing what the function is supposed to do is a prerequisite for writing the function in the first place. So that's test-driven development, where you start with the tests before you even bother writing the function. That's not necessarily a good strategy, it's just a strategy for programming. So for next class, definitely go and explore the GitHub repo, specifically under the tests right here. And have a look at all the tests. We can go back to, the functions topic. What's this, topic 2 of the whole course? Here's a bunch of unit tests for everything we did in that topic. Test Celsius to Fahrenheit, positive Celsius value returns correct Fahrenheit value. These tests would have been a really good candidate for subtest, but whatever. Celsius to Fahrenheit, negative Celsius value returns correct Fahrenheit value. Float Celsius value returns correct Fahrenheit. Positive. Oh, now it's square of sum tests and so on. There's unit tests written for every function we wrote in the course. Not just assert tests, actual unit tests. Go and look at them. It's a great way to learn how to write these things. Any questions about unit tests? Yes.
So before you said that unit tests, like you can write a unit test, but you think you could be right, but you could still be wrong. Do you have an example of like when a unit test would pass, but still your code is like incorrect?
Well, it might be that often what that usually means is your unit tests weren't really thorough enough. Or sometimes there's some functionality that's just really hard to test. And a lot of times that functionality is the consequence of side effects. And that's why we avoid side effects in our code if we can, because it becomes a lot harder to test those things. A lot of people don't really think about it like this, but any input-output, if your function's doing input-output, that's kind of like a form of side effect. In assignment 2, there were some functions that generated plots for you, right? That's a form of like a side effect. And those things are very difficult to test. So that's also where just things that are difficult to test might get missed in the test, or maybe the tests just really weren't thorough enough and some funny edge case got missed. That's where you really can't be convinced, because you would have to, in order for your tests to prove to me that your code is correct, you would need to prove to me that your tests are thorough enough. And in order to prove to me that your tests are thorough enough, well, good effing luck, because you just can't. Yeah. I mean, interesting question. But that said, that's why we take our time, write our tests, to help demonstrate. It's about convincing ourselves and other programmers that it's correct. Realistically, too, if you're a programmer and you're working on a team with other programmers, you're going to use something kind of like GitHub, if not GitHub. Actually, most likely GitHub. And anything you do would be like what I have you doing in this class if you want to make any change to the course content. You submit that pull request thing. You submit a pull request. Oh, I wrote a new function, and I want to submit it to the code base. Or I updated the course content, and I want to submit it so it gets updated. You submit the pull request. Another programmer would come along and look at what you wrote. And the purpose of that is not for the other programmer to be like, you're wrong, oh my God, you're... No, it's for having another separate set of eyes. Sometimes as a programmer, you kind of get like tunnel vision on what you're doing. You forget something. Someone else with a fresh set of eyes thinks of something else that maybe you didn't think about. It's really important. But the other programmer might look at what you wrote, and they'll look at the tests you wrote. If you didn't write the tests, they're going to be like, write the tests, because I don't want to look at your code. I want you to write the tests. I want to know that the tests pass before I start even looking at your code. And then I'll also look at your tests, and I'll be like, you know what, your tests missed this particular case. Write a test for that case too, just so we know you're right. And the value too of having the tests is if someone else comes along and says, oh, that function that you wrote, I'm gonna update it. I got a better idea. I'm gonna improve it. And they make some changes to that function that you already wrote. Well, the tests you already wrote will get run on their updated version too. And if they pass, pretty good. If not, well, maybe something's wrong. I saw another question. Someone over here had a hand up about unit tests.
I think my question was answered.
Cool. Any other questions though about unit tests? Write them. Do them. They're good. They're great. They're better than assert tests. We started with assert tests because they were accessible. Right? You don't need to know a lot in order to write your first assert test. Assert, some statement is true. If it's not, it crashes. With unit tests, there's a lot you kind of got to know. A lot. Including what the hell a class is, which we only just recently learned about, because the unit tests exist inside a class. So now that we know what they are, we can start to play with unit tests. A lot of the unit test stuff is going to be a little bit like magic code. You just got to write it this way to make it work. But a lot of it's like that to me too, because I don't know the ins and outs of the actual unit test package. I just know how to interact with it. So as long as you're familiar enough with it to interact with it and write your tests, you're good to go. So no other questions about unit tests, really? Who here has found that the tests, I'm not specifically talking about unit tests or assert tests, although I suppose this would be overwhelmingly applicable to the assert test because it's what you're used to. Who here has felt that having the assert tests for every function you ever wrote, whether it's on assignment or something we did in class, who here felt that those assert tests really helped along the way? Yeah. How many people here wrote a function and the function passed 8 out of 10 of the assert tests and then found that, oh, it failed on this case. Oh, I see what I did. How many times that happened to you? Yeah. The tests are there to help you, to help other programmers know that the code is correct. Great. Because also, like, imagine submitting an assignment. You get, like, look, when you submit your assignment and all the tests pass, you're pretty damn confident you're going to get a damn good mark on the assignment, right? We are so lucky in computer science. So a lot of people don't think about it. I know I've talked about it a lot, but a lot of people don't really think about it. Computer science, it's just math, but we trick you into doing it. So it's just math. But unlike your typical math class, whether it's algebra, calculus, whatever, you get a problem, and you follow the process. You get a problem, you read the problem, you do all the work, and you get your answer. And then the question, like that begs the question, well, is it right? And you go, I hope so. Next question. For us, we can check if it's right. We're spoiled. And if you haven't been taking advantage of the fact that you can check if your functions are correct, you can check if the work that you did is correct. If you haven't been taking advantage of that, what are you doing? We're lucky. Take advantage of it. I can see the people in this room right now, you're all pretty good at this stuff. Keep up the good work. Keep checking that your stuff is right. You're good to go. You're going to crush it. I know I've asked this a bunch of times. I'm just curious if it's changed. Raise your hand if you are going to take 162 next semester really high. Really high. So let me start alienating people. Neither of you are? What are you doing? Why aren't you?
I still need to change it.
Oh, you got to change things around. Oh, okay. All right. How about you? Why aren't you taking it?
I'm not sure.
You're not sure. Well,
I might still.
you might still. You should. If you find, let me put it this way. If you find that you kind of enjoy this class, if you find like solving the problems a little bit fun, now fun, just because you find it fun doesn't mean you don't find it challenging. Yeah, raise your hand if you find this course challenging. Yeah, it's supposed to be. Unlike a lot of other disciplines, if you don't have experience with this stuff, you're jumping into the deep end with a new topic. If you've never taken biology before, but you've taken your other science courses in high school and you'd have to take first year biology, there's a lot of transferable skills, right? You can probably do reasonably well in biology. Computer science, there's no other, the closest thing you have is grade 12 math, right? Unless you took a programming course, but often the programming courses in high schools are terrible. And a lot of time they set you up not for the best success. So you're jumping in the deep end in a brand new topic. It's going to be challenging. I'm using the word challenging instead of hard because those aren't the same thing. Nuance difference. But if you find that you kind of find it fun, I've had students tell me, oh no, I can't take 162 because I find when I'm working on the assignments, I'm just having too much fun. And I'll spend all this time on these assignments playing around with them, and it's distracting me from my real courses. And I think, this isn't basket weaving. This is computer science. This is one of those disciplines that students covet. As wow, you took computer science? Whoa. You do that? Oh, you're going to be rich. Yeah, you will. Just don't be a prof. If you find it fun, if you enjoy working on it because of the puzzles and whatnot, if you enjoy it, people would say you're lucky if you enjoy it. And I'd say that to you too. If you enjoy it, consider yourself lucky. A lot of people don't. A lot of people can't do it. At the beginning of the semester, on the first topic, I have a thing where it's like, is this course hard? And I'm like, no, no, no. I lied to you. This is a very challenging course. But if you made it to this point and you're enjoying it, take more. Do it. If after 162 you don't like it, fine, fine, you don't like it. If you do, take another one. Next thing you know, you've got a degree and you work at who knows where, making twice as much as I do first day of the job. I'm not joking. And these are the types of jobs that they're happy to have you work remotely. You want to live in Antigonish the rest of your life, being a programmer for a company in Seattle? Cool, whatever. Get paid those American dollars. Yeah. All right, any last questions before we wrap up for the day? Yes.
It's not on topic, but do you write your code for GitHub in PyCharm and then transport it to GitHub?
Typically, yes. So most of the time if I'm writing code, it's not going to be in Colab. Colab is fantastic. It'll be in like your IDE, and then there's a way you like upload it there. Now on GitHub, there's a way to make edits on GitHub. That's for like quick and dirty ones. But if you want to start making like significant changes, you're going to want to do it locally, and then you do what you call like push the changes to the remote branch, and then that's where it gets updated.
Because, well, the thing when you have the import in your IDE and then you remove it in Colab, would you have to do similar stuff like that when transporting code from an IDE to GitHub?
No, with GitHub, it's going to assume that you're going to be using an IDE like, yeah. Well, we can talk about all that a lot later anyways. All right, cool. I'll see you all later.